Alright, so this test we're going to be doing today is the Kruskal-Wallis test. Kind of irritated with myself. I had this all done up the other day, and then I screwed it up when I was uploading it. So, I get to do it again. Yay! Anyway, the Kruskal-Wallis test is the non-parametric version of ANOVA. And it's just one way ANOVA. Okay, so the idea is we have, three or more categories, and we want to know, is there a difference between them? Okay, now, obviously there is a reason why we would use Kruskal-Wallis versus, there it is, versus ANOVA, and that's because, again, the data is not, any way normally distributed in any way. So, of course, there is no difference in whatever due to the group that it's in, if you will. And of course, with ANOVA, we were discussing about the amount of tomatoes that you'd get based on what fertilizer you used, or things of that nature. So of course, at least one is significantly different. So then, a lot of you would be thinking, well, we're going to do a follow-up like the Tukey? And the answer is, well, no. There is no follow-up for a non-parametric test. Okay? Again, they are not as good as our parametric test when we can use them. And so here's the deal. And so I'm just going to type this out. I think, it seems like to me anyways, that the different kind of shoes might be such that there might be a difference based on there's no difference in mile times between shoes, or due to shoes types, brands, whatever. Okay, and of course that's our H0, and of course H1, of course there is. So when I think about that, I think to myself, well, I wonder why that would be, maybe. And then something that occurs to me is, well, oops, yeah, so why didn't that show up? That's weird. Oh, don't wrap it. Here you go. And of course, at least one is significantly different. Now, but why might there be a difference? Well, because maybe the people that, use New Balance shoes, for instance, are just your weekend, like your old grandma lady, I don't know, that wears her shoes to go for a walk. She's not really running miles, someone like myself who's kind of fat and old and doesn't, well, I don't run. I couldn't run a 6-minute mile if the devil himself was chasing me. But the idea is there might be a difference in the kind of people who buy the shoes. All right, like Adidas might be more your soccer players, maybe not the long distance runners, but maybe the Nikes are. Who knows? Okay. So what we're going to do is we're going to put Nike here, and we're going to grab Nike's shoes. We're going to, or shoes, I mean, we're going to grab Nike shoes. We're going to grab Nike's times and paste them there. And then we're going to do the same thing for Adidas. And we're going to grab their times. And we're going to paste them right here. And then we're going to do a New Balance. And again, nothing against New Balance, just saying, oops, be aware that, what is going on here, yo? Be aware that different shoes, are typically worn by different kind of people. So would it shock me to see that certain shoe companies would have their people that wear their shoes run, on average faster? No, not really at all. Okay? So what we're going to do here is we're going to come back and we're going to rank these guys. So we're going to go equals rank average. There we go. So we're going to rank this guy, right, with respect to this column. Make sure you hit F4, and we'll do it in ascending order. Boom. And we're going to paste that down. Again, you can do this several ways if you like. The easiest, I think, is just to go equal sum the Nikes, come down here, sum the Adidas, so equal sum of the Adidas, and then equal sum of the New Balance. Oops, I said of the New Balance. There we go. Now, in a class where I spend a lot of time with pivot tables, I probably in this situation would do it with a pivot table to add those up. Now, the Kruskal-Wallis test turns out is a chi-square. It's based on a chi-square, and it's an upper tail chi-square, and that is, it's over here. And the degrees of freedom are k minus 1. So if there's 3 groups, 3 minus 1 is 2 degrees of freedom. Now you're like, how do we figure this out? Well, it turns out it's also called the H test. That's why this H equals. That's our test statistic. You don't want to question on that. Just be aware of it. That's a fact. So n plus 1. All of a sudden I'm doubting myself. Well, I know what the rest of the next part is, but the next part, it's the next part after that part that I start doubting myself on sometimes. So I'm going to look it up just so I don't screw it up. Yep, I was right. Okay? So then it's R1 squared over N1. R1 being the sum, for in this case, of the Nike shoes, N being the number of Nikes. Let me clarify that this is just N over here. It's just N. So by saying just N, what I mean is the total number of runners that we have talked to. So your book makes a big deal of making this cap N. So just be aware of that. This is R2. This is for the Adidases over the number of Adidas plus R3 squared over N. 3 minus 3 N plus 1. Okay, so let's start plugging this in. So, first of all, it's 12 over, and I'm going to use parentheses on the bottom like so. And so back over here, there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 is my N. Okay, so I'm going to do 14 times 15. Okay, times. And now the sums are, give it to me. The sums are 12.5 and 37. I'm going to write those down. So 12.5 squared. This is 37 squared. There were 4 in the first one. There were 5 in the second one. And there were 55.5 over 5 again, minus 3 times 15 n plus 1. Now I'm going to break out my calculator and I'm going to show you this with my calculator to make sure I get it typed in correctly, to make sure you get it typed in correctly. I hate people. I hate it when people make dumb mistakes. I hate when I make stupid mistakes. By the way, I've made them all, so don't feel bad if you make a dumb one, because literally I've made them all. Every stupid mistake that can be made, I've done it. Sadly, more than one time. So 12 divided by parentheses, 14 times 15 parentheses, times parentheses, and then 12.5 squared divided by 4 plus 37 squared divided by 5 plus 55.5 squared divided by 5 parentheses minus 3 times 15. Cross your fingers. Boom! 8.08. Nice. 8.08. That's great. Now we need a cutoff score, yes? So if I'm going to do it on Excel, I'm going to do equals chi-square inverse, and it's 0.95, right? So 95% less than that, 0.05 above it, and 2 degrees of freedom. 5.99 is my critical value. Oops, come back here, you hippie. So, back up here, 5.99 is our critical value. And we are, as you see, out here somewhere. Whoa, whoa, what the heck? That's weird. So our decision would be to reject H0. What does that mean? It means there is a difference in the time Now, would that be average time? No. It would be the median time. There's a difference in the times of the miles that are run by the wearers of these different shoes. And yes, at least one of them is significant. Okay? Again, could be all three of them. We don't really know. Now, interestingly enough, if you look at the original data, okay, this one here doesn't look that abnormal. And you're like, I'm not sure nothing really strikes me as being weird about this data. And you're right, I don't know that it does either. In other classes, when we get into non-parametrics more, which for most of us, thankfully, in our daily lives, the kind of stats we will do will not be non-parametric. We'll do a lot of parametric data. But if you're going to do non-parametrics, you do a lot of tests to see if this fails, being normally distributed kind of thing where we can just do an ANOVA. Okay? But again, look what would happen if we did an ANOVA on this. So our input range would be these guys. Remember, it's an unbalanced ANOVA. And I put my output down here. And this would be interesting to see what happens here. Look at your p-value on this guy. Your p-value is 0.04. 0.004, I can't see. 0.004. So clearly there is a difference, okay, even if you were using an ANOVA in this case. But again, in this book, the book just waves their hand and they show you the ideas of non-parametric tests, but they don't really get into a whole lot of why we would test that. And it's kind of beyond the scope of this class. So what I did was I made up a test. I made up one where I hope you can see this one looks a little goofier. These are all in the 30s. Oh, what's up with 11? That's kind of weird. It kind of skews my data. Look at all these in the 30s. Oh, this 54 is kind of screwing with my data. That's weird. And so because of that, what we're going to say here is that this one probably would fail the assumptions that we'd need to make to use ANOVA. We'd be careful about this guy and that guy. Would probably throw us off enough that we'd probably want to be careful, and we'd probably want to use, okay, the non-parametric test. But I'm in the mood to do an ANOVA first, so this is a good review, I'm just saying. But in Chapter 13, you will be doing just, oops, stop it. You'll be doing just the Kruskal-Wallis test in this case, okay? And, yeah. And interesting to note, what you see down here is, oh, look at that! You failed to reject. Interesting. Interesting. I wonder what will happen when we do the Kruskal-Wallis test. So again, oops, wait a minute, stop it. Okay, so there they are. Now, there is a way to actually rank them. Now, you could rank them in theory just the way they sit. I don't like that. It takes too much fancy dancing in your Excel to pull that off, and I'm just not a big fan of teaching kids really wildly strange things. This is not wildly strange at all. You simply take the rank average of this guy with respect to the column that it's in, F4, comma 1. And so that is the lowest rank. Big shock. I bet 54 is the highest. Oh, it is? What? No. So remember, there's 21 data points. Each one of them has 7 in it. So keep that in mind in a minute. So we're going to sum up all the Seattles. We're going to sum up all the Portlands. And again, there's a fancy way to do the averages. There's several fancy ways to do the sums. But this is, I think, the easiest. Just equal sum. And then just click and highlight San Francisco ones. Done. So 91, 58, 82. At first blush, one might think that that seems like there probably is going to be a difference. And I would think that that probably is true. Now remember, we failed to reject We failed to reject H0. That means we said there was no difference if we used an ANOVA. But we're pretty sure in this case anyways, and pretty positive, we're going to want to make sure we use the Kruskal-Wallis test, because our violation, I think we violated our premise, that is, that this data is skewed enough. We have to be careful. So 91, 58, 82. 91, 58, 82. I have Alzheimer's a little bit, so I can't remember things, so I have to write them down. Otherwise, we'd be going back and forth 100 times. Minus 3 times 22. Again, there were 3 groups. K equals 3. So our degrees of freedom will be 2 again. Oh, by the way, that means our cutoff score is the exact same cutoff score as last time. Okay? So let's whip out the old calculator here. Oops, come back here. Stop it. So on 12, divide by 21 times 22 times parentheses 91 squared, divide by 7 plus 58 squared, divide by 7 plus 82 squared, divided by 7 minus 66. Yes? Oops, darn it. 2.159. And look at that. Our decision is exactly the same. We're in here. That's what we'd expect to happen if what? If there was no difference between the two of them. And so, as a result, we'd fail to reject, and we'd say there's no significant difference in whatever it is we were ordering. I don't know, let's say orders of fish and chips, I don't know, in each of those 3 cities, okay? There's no significant difference. That's how the Kruskal-Wallis test works. It's pretty straightforward. Again, it is just the non-parametric version of ANOVA, and that's it. And there is no follow-up to it. If you reject, that's it, you're done. There is a significant difference. At least one of them is significantly different, but you don't need to follow up with it. There is no Tukey test. There's no Chaffee test. That's it, you're done. Okay? So that should get you started, I think, and, well, honestly, finished with it, too.